Question. If the strike were to start on the 6th, is that the day of the 72 hours notice, or is that the day the strike starts? 72 hours notice.
So you wouldn't come to school on the 6th?
It'll be very clear if it happens.
It'll be like Saturday.
All right, guys, let's get going with some more restrictions. Going to introduce you guys to more restrictions on what I could throw at you in a permutation question, right? And we know that restrictions, does order matter when I throw restrictions at you? Yes. When you're arranging something, right, order always matters. Okay? This is going to become very, 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 very important when I start giving you questions that order doesn't matter. Okay? But today, order still matters. We're arranging objects, whether they be letters, be people, whatever the case may be, we're ordering something, right? We're moving them around, we're changing the position of them, right? So, more restrictions. Okay, so example 1, some of this will be exactly what we've done already. So here it says, in how many ways can all the letters in the word oranges be arranged if there's no constraints, right? So this one is just like last class. So how many letters, first of all, are we dealing with? Right, so there's 7 letters. Right, so those are our objects. We have 7 letters. Those are specific letters from the word oranges. So if there's no constraints, right, what would be a fast way to show me, not the actual answer yet, but how I can display what it equals? Perfect, exactly. So this is 7 factorial. But as I promised you guys last class, I'm going to show you everything that means the same thing so you guys get used to equivalencies. And what's the other way that I didn't write down yet?
The formula.
Which side of the formula? Right, 7p7. Right, so all of those things mean the same thing. Right. So then from there, 7 factorial, so 5,040. Right, and then next one, so that's nothing new. Okay, next one's not new either. Not new. It's been a struggle speaking this afternoon. It's been a day already. All right, try that again. First letter must be an S. Have we done ones like this already? Yeah. So this is not a new constraint, right, or a restriction. So this would now just be, sorry. So if you picture it, 1, 2, goodness gracious, 1, 2, 3, 4, 5, 6, 7. So if the first letter must be an S, that's a 1, and then times 6. And could I just say 6 factorial would be my answer? You could. I just like showing, so why is it 6 factorial? Where did the other letter go? Right? And again, as soon as there's restrictions, I like laying it all out so I can see the things that disappear, right, when they get multiplying. So if you have the newer operating system, you can just cheat, go grab the 7 factorial and replace the 7 with a 6. Just saves you a little bit of space on the calculator. So 720. All right, so C is the first one that's a little bit new. Okay, so I haven't done the restriction where I start putting things together. Okay, so here it says the vowels must be together in the order O, A, E. Okay, all right, so 1, why it does that, there we go. 1, 2, 3, 4, 5, 6, 7. So think of them as being one tile now, because do they have to stay together? I put them on the far left right now, but again, do you guys realize they don't have to be on the far left? They just have to be together. So basically, the way I do these questions is I do one case, and then I times by how many positions those vowels can move. is the easiest. Okay, does that make sense? All right, and that's why if they are together, I just start on the far left because then it's just easier to count the positions. Okay, well, we're going to talk about that. So it has to be an O and A in that order. So if they have to be in that order, how many choices for the O? 1. A is 1 and E is 1. Right? How many letters are left over? 4. So then it's 4 times 3 times 2 times 1. Now you could do all the cases, right, like I showed you guys last class, but it's just easier to figure out how many cases are there, which in this situations, how many places can that O, A, and I move between all the leftover letters? So how many places can they all move? How many positions? Do you guys all see it's 5? It's always going to be one more than what's left over, right? Because a lot of times students think, oh, it's 4. But if you say it's 4, you didn't count that it could be at the beginning. So some of you are looking at me like you don't know what I'm talking about. So do you agree that they could be at the beginning? Could they go in between these 2 letters? Could they go in between these 2 letters? Could they go in between these 2 letters? And could they go at the end? Count the highlighted spots. There's 5 different spots that this tile can move, right? So O, A, E can move. It could be at the beginning. It could be between the first and second. It could be between the second and third. Could be between the third and fourth, right? And it could be at the end, right? So with that in mind, like I said, you either draw them all out, all different 5 spots it can move, or you can just take this and times it by 5 cases, or if you want to say 5 positions, whatever the case may be. Right? Do you guys agree cases, position? What word would you actually what would you guys prefer? Cases or positions? Cases, sure. So there is 5 cases that can happen, right? Because they can move 5 different places. All right, so would you guys freak out if I did this? So this is the same as 5 factorial? Okay, guys, so the ones that are like, what? Watch, you people. If you type this into the calculator, are you not going 4 times 3 times 2 times 1, enter times 5? Because that's what the diploma is going to do. They're not going to say 4 times 3 times 2 times, or they're not going to go 4 factorial times 5. They would never do that. They're just going to say 5 factorial. If you did this on a quiz like this, though, is that okay? Do you have to show me 5 factorial on a written? No, because that still shows me, right? But they will never on a diploma, if it's a multiple choice question, they will say 5 factorial. Because it's equivalent, and they just want to put it together. Even though you guys, I understand why you are like icking on this, because you're thinking 5 factorial, right, is you're thinking the 5's at the beginning, right? But it's 4 factorial, right, times 5 cases, which is the same as 5 factorial. So don't freak out if the diploma does that, okay? Right? Because like I said, this kind of shows you beautifully, okay? Lays it all out for you. But like I said, and again, if you wrote 4 factorial times 5, would I mark that right? Yeah, it's equivalent, right? So as long as whatever you write's equivalent, even the diploma wouldn't care on a written, guys. If on a written you did this and you said times by 5 cases because the vowels can move 5 different positions, are you still getting full marks on the rubric? Yeah, you're still getting full marks, okay? It's just, like I said, I'm going to show you equivalencies. This is equivalent to that, so both are acceptable as final answers. Well, final answers will be so 120, so 100, oopsie, so 120. So this is one of our new restrictions we're doing today, guys, is when I put objects together where they can't separate. Okay, so think of them now as its own algae tile that has to move together. Okay, so now it says the vowels must be together in no particular order. So the only difference is, what are those ones going to change to? 3, 2, 1. That's it. Is everything else exactly the same? Yes. Right? So 1, 2, 3, 4, 5, 6, 7. So the vowels still must be together, but it's saying no particular order. So this now changes to, like as you guys said, 3 times, 2 times 1. So again, I put them at the beginning. They didn't have to be at the beginning. So the leftover letters are times, oh, would I got marks taken off on my rubric? Probably would have. Ooh, I forgot my one little multiplication symbol. Oh, thank you. Okay, so 4 times, 3 times, 2 times 1, times, still 5 cases. So with that, how else could I write that?
5 factorial times 6. Oh, 6 factorial. What is 3 times
Where are you? What are you talking about?
3 times 2 times 1 is 5 cases, and 3 times 2 is 6. It's 6 factorial.
Oh, interesting. Huh. The diploma will never do that. But interesting, Sean. I love it that you just thought that. Yeah. The diploma will not do that, but 100% agree with you. I shouldn't say they never will. The diploma always surprises me. I've never seen the diploma do that. I've seen the diploma do this. Which technically is 6 factorial. Right? Because if you go 3 times 2 is a 6, times 5 times 4 times 3. Interesting. Love it. I've never had a student say that before to me. Look at you. That's where you're going to? That's so cool. Right? So again, does everybody see what Crazy did? That was a compliment. Okay? Right? Does everybody see that that could happen? Right? 3 times 2 is 6. Times 5 times 4 times 3 times 2 times 1. So technically you could write that as a 6 factorial. All right. So questions so far, guys? So only kind of 2 questions that were a little bit different than what we've done so far. All right. So example 2 says 5 people, Shay, Reese, Caddison, Matthew, and Simone, are seated on a bench. In how many ways can they be arranged if Matthew must be seated in the middle? So we've sort of done this before. So how many people do we have? 5. So 1, 2, 3, 4, 5. So Matthew must be in the middle. So then we only have 1 choice for the middle. So we deal with that first. And then the rest don't matter. So 4 times 3 times 2 times 1, which would be the same as 4 factorial. Which is 24. Now, Shay and Caddison must be seated together. So 1, 2, 3, 4, 5. So Shay and Caddison together. So how many choices for the first position? 2. Because again, it doesn't say which one goes first. So you do have to go 2 times 1. Okay, and they're now 1. I have them at the beginning, right? But we know they're going to move. But before we do that, there's 3 of them left over. So 3 times 2 times 1. And how many cases? 4 cases. Right, so again, 4 cases does not mean 4 factorial. Just there's 4 cases, so you can do the 1 case and times it by 4, because all the cases will be the same. Do you guys agree if we laid it all out and actually moved Shay and Caddison to the different positions? All the number multiplications are the same, so we don't need to show them all. So this would be the same as this one we can't get funny with. So 4 factorial times 2 factorial, which would equal 48. Just a 2? Good. Like I said, as long as you write something that's equivalent, I'm marking it right. All right, so this is the one that gets a little tricky, okay, if you try to do all the cases. Because here it says Shea and Caddison cannot be seated together. So don't write this down. Okay? But if you're thinking about this, 1, 2, 3, 4, 5, could you kind of go through and try to do all the cases? Right? And so forth. But that is the long way of doing this. Okay? If they talk about somebody not being together, it's way easier to. Exactly. Okay. So what Julia just said is you take the total ways we can arrange these kids, okay, without any restrictions, and you subtract it, right? Not that. You take that number and you subtract how many ways they can be together, right? Because if you find out how many ways they can be together, which I did purposely, there's 48 ways for them to be together. The rest of them will be them not together? Yes. That's the way faster way of doing it. Okay. So that's what we're going to do. We're going to find total arrangements with no restrictions on or any of the kids. So total arrangements. So this is kind of what we're thought process. So it's total arrangements with no restrictions. Right, and we're going to subtract Shea and Caddison together. Can we all picture that that would work? Okay. So we know total arrangement with no restrictions. How many kids are there? 5. So no restrictions would just be 5 factorial. Minus, since we cheated already, we're using B. But if B wasn't done for us already, right, that's what we'd have to do, is we'd have to figure out Caddis and Shea together. Right, but we can, I'll do this. Look at B, right, so then it would be 5 factorial minus 48. So 5 factorial minus 48. So 20, 60, 120. 48, so 2. 72? That was weird to me for a second. Ugh. So there's 72 different ways, okay, that they could set it up so they're not together. Okay. So again, could you technically write all the scenarios down and add them all together? Yes, but it's not fun. And this one, there's only 5 people, right? A lot of times there might be 20 people, so it gets very, long if you're trying to visualize all the cases. All right, so for this one, here it says, how many different 3-digit even numbers greater than 300 can you make using the digits 1, 2, 3, 4, 5, and 6? No digits, repeat. Okay. Yeah, I'm going to lead you guys through. Well, yeah, I'm going to help you with this a little bit. Okay? Because if it's a 3-digit even number, do we have a few things we have to worry about? Okay. All right. Right? So how many different 3-digit even numbers greater than 300? So if it's greater than 300, actually I'm going to show you the cases for this. Otherwise I lose students if I go right to the little trick. Okay, I'm going to actually do the cases because there's not that many, in the sense of if it has to be, because it says greater than 300, so the first one has to be a 3, a 4, a 5, or a 6. Do you agree that those are all the cases I can do? Okay. Everybody see that? Does that make sense? Okay. So I'm showing all the cases, because when I don't, students are like, huh? Okay. So it's saying I have to have a number greater than 300. So those are all my cases. So what do I put in place of all those? How many choices if I only can put a 3 there? 1, 1, 1, and 1. So the next restriction I'm going to deal with is they have to be an even number. So guess where I have to go to next? I have to go to the end, right? Does the end of the number tell you, bless you? Does the end of the number tell you if it's even or odd? Yeah. So if it starts with a 3, I can use a 2, I can use a 4, or I can use a 6. So I have 3 choices. Okay. So then how many left over do I have for the middle? So I've used 2 numbers. So I have 4 because they're, nope, digits 1. I should put that on the same line. Oh yeah, so yeah, there would be 4. Duh. So I have 4 left because I took 2 away. I couldn't count. All right, so this one is going to be 12 different 3-digit numbers greater than 300 that are even, right? Only using those digits. So now if it starts with a 4, see how this scenario is different? Right, so this scenario is different. So you had to do a case where the first number was odd and a case where the first number was even if you were trying to simplify this and not look at all the cases, because it would affect it. So if it starts with a 4, I only can use a 2 and a 6. So this would be now a 2 choices, and then still in the middle, 4. And is the next one going to be the same as the first one I did? Right, because if it starts with a 5, the end can still be a, exactly, 2, 4, 6. So this can still be a 2, 4, 6. And then my last one is like my second example. And so then this could be a 2 or a 4. So I only have 2 choices and then still 4 numbers left over. So then my total is 40. Right, so with this one, in the past, I've went to, we can set up 2 cases, right? Because I know that if it starts with a even, I have less choices at the end, right? But if it starts with an odd, I have more choices at the end, right? Doing that with students without the visual the first time never goes well, right? And understandably so, right? It's hard to visualize that without seeing it laid out like this. But now that you've seen one, okay, if you get one similar to this, you might want to, okay, or you could lay out the choices. And the thing is, if there was lots, guys, and you did all the choices, are you going to start seeing the pattern? Yeah, and you'd go, I don't need to do all this. I can put all these ones together, okay? This would be considered a standards of excellence question, right? This would be a harder style question in this chapter. Okay. All right, so let me just finish this. So 40, right? Different numbers that are even, greater than 300 using those digits. All right, so last little thing for restrictions that I'm going to show you guys. Up until now, you might not have noticed, but every single question I've given you that has objects in it, none of them were the same objects. If you guys go back and look at the words I gave you guys, none of them had repeating S's or repeating E's or repeating A's, okay? Is there a ton of words in this world that have repeating letters? Yeah, I say it's harder for me to find a word that doesn't, right, than a word that does, okay? okay? It's tough to go, okay, I can't use that word, like at the beginning of these lessons, okay? So that was purposely done. Because if there's repeating letters, if I flip them, is it still the same arrangement? It is. So there's just a quick little thing you have to do to get rid of the repeating arrangements. So I color-coded this so you could physically see what I mean. So using the word pool, right? So with those two O's, right? If I flip them, is it the same arrangement? Yes. Right? And if I start moving the letters, like I said, if I keep flipping and moving those O's, you end up getting repetition of the same arrangement. So what we have to do is divide it out, okay? And it's just a quick division. So if there's two O's that repeat, you just do your question like normal. Pretend everything's different. Every single question, guys, I pretend at the beginning, every letter's different. And then I deal with it at the end. If you try to deal with it within the question, it gets way too confusing, okay? So just deal with it at the end. And this is all you have to do at the end to deal with it. If there's two repeating letters, you divide by 2 factorial. Because there's 2 ways, right, that you can arrange those 2 O's. If there's 3, if it was pool, right, if there's 3 O's, guess what you'd have to do? You'd have to divide by 3 factorial, not just a 3, because how many ways can we arrange those 3 O's? 3 times 2 times 1, which is 6 ways. So there would be 6, right? A grouping of 6 that you would have to divide out. That would be all the same, okay? So do you think you're going to have multiple letters repeat in a word? Yeah, just think, mathematics. Is there multiple letters that repeat? So you just divide out how many there is, okay? So it's just a quick extra piece that you have to remember. So this part of the restrictions, students don't find hard. They just forget to do it, right? They just quickly do the work and then they forget about the repetition, okay? Because the work, how we set it up, guys, is exactly like all the other questions, is just at the end, there's a division part that you have to do, okay? To make sure that you don't count, like this first one, you don't count that twice. Because right now, if you just go 4 factorial, there's, right, 4 times 3 times 2, there's 24 different ways you can arrange the letters in the word pool. Do you guys agree? Yeah, but is there a bunch of them that are repeating? Yes. So dividing the 2 factorial in that situation is a 2, cuts them in half because there is 2 repeating letters, right? So it gets rid of, basically does this. No, we aren't going to count all this second line because they're the same as the first line. Okay. Right, so that's what that's all talking about. Okay. To eliminate the repetition of arrangement, you just divide by the repeating objects. Okay, so if there's 3 repeating objects, you divide by 3 factorial. If there's 5 repeating letters or objects, you divide by 5 factorial, right? So I'm just going to do a couple really quick with you. Because again, they don't make it harder, it's a remembering thing. So how many different 8-letter arrangements can you make using the letters of the word aardvark? So how many, well, 8 letters. So we have 8 letters. So normally we would go, oh, 8 factorial, move on, right? But now we know we can't do that because we have repetition. So, whoopsie. So all of these A's, how many A's are there? 3. So then, how many ways we can arrange 3 letters? 3 factorial. So we have to divide a 3 factorial out because when I move those A's, it ends up being the same, right? And what else do we have repeating? R. Right. Right. So how many R's do we have? 2. So that's all you got to do. Right. So, but guys, please tell me, does that make sense? We have to do that, right? You guys can all visualize if I move the A's around, like in all those spots, it's still aardvark, right? There's 6 different ways I can move those A's, right? And still get that position that's on the board right now, right? So, and then the other thing that you have to be careful of is this. Not very often, but I still have students I need to talk about it. So 8, you guys are going to tell me my mistake. Oops, not that. That's 4. Everybody see the mistake that? Okay, good. So please make sure, especially if you guys have the newer operating system, can you put it right into a fraction to begin with so you don't have to worry about brackets? Right, because if you just go 8 factorial divided by 3 factorial times 2 factorial, does the division, then times. So either, this is your choice, use your fraction button and put it already in a fraction form so you don't have to worry about brackets, or just make sure you bracket the bottom, right? And then you'll be good. I'll just think 8 factorial is already a big number, so that broke it down quite a bit, right? Because it went from, so just to show you guys, so if they were all different, right, there's over 40,000. So having those repeating letters break it down a lot. All right. Dun, dun. So this little guy here just says, how many different 5-digit numbers can you make arranging all the digits 17171? So again, how many letters are there? So again, treat them like they're all different. So 5 numbers, so 5 factorial over 3 factorial, 2 factorial. No. This one should make sense, yeah, that there's not going to be, oh my lord. It'll be 10, won't it? Yeah, I can do this in my head if you think about simplifying it. Yeah, because technically, should you have been faster than the calculator? I shouldn't have grabbed the calculator, because 5 times 4, 3's factorials divide by 2. And me, instead of going ding, 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 yes, is way worse putting it on the calculator than just using our brains and simplifying that in our head. Ooh. All right, so last one that's a little bit like kind of funny looking, that is interesting, is if you have a grid, right, and you have to go from one point on straight lines, or it doesn't have to be straight, just lines, okay, to the other corner, okay, you can actually use this technique to be able to do it, okay. So I'm going to show you 2 ways to do this. The first way is using what we just learned. So with this one, it just says, how many paths can you follow from A to B in a 3x4 grid if you can only move up or to the right? That's important. You can't go any direction, otherwise there's infinitely many solutions. So we can only move up and to the right. So if you use what we just learned, you have to picture how many ups can you go? You can do 3 ups. So 1 up, 2 ups, 3 ups. I'm just saying, how many ups can you do?
Oh, that is.
No, you're starting at A. No, you're going from A to B. How many paths can you follow from A to B? All right, so we can only move up and to the right. So we're starting at A, moving our way to B. So I'll actually do the pathways the second method, okay? So right now I'm just asking, how many ups can you do? Not in total, just ups from A. You can do 3 ups. So I'm using U for up. I have 3 ups. How many rights can you do? Right, we can do 4. So 4 rights. Arrange those letters. So how many letters in total do we have? 7. factorial over my repetition of ups and rights. So how many ups do I have? 3 ups and 4 rights. Okay? And you're like, really? That works? And I'm going to show you it works, so you believe me, because isn't that kind of weird? Right? But it works, and I'll show you in a second. So you're trusting me right now, but I will prove it to you, because it is strange. Okay? It does have to do with pathways, so I am going to show you a little bit of pathway work. Was in the old curriculum. Okay? All right, so 7 factorial divided by 3 factorial 4 factorial. So you guys are trusting that this crazy math works, but I will prove it to you. So there should be 35 different ways that you can get from A to B, only moving up or to the right at any one time. Okay? And again, by doing this, did you get to see any of those pathways by me doing that math? No, you got to see no pathways. You just are trusting that there's going to be 35 ways. Okay? I'm going to show you those 35 ways by a pattern. It's going to be quick. So, and you technically could do this on a quiz if you rather did this, but it's not curriculum. We used to do pathways. Now we just use permutations to do this. All right, so if we can only move up and to the right, I'm going to do each part individually. How many ways can I get there from A? Using numbers now. How many? I want to hear. Don't get ahead. How many ways can I get to this corner? Think of this as blocks or something. There's one way to get there. How many ways can I get there straight walking? 1. How many ways can I get here straight walking? 1. Because again, I'm not stopping, just how many ways? Direct path. So I can only move up and to the right. So there's only one way I can get here. I can't get there going this way, because would I have to go backwards? Yes, I'm walking to, think of these as corners, to the end of that corner. So again, there's only one way I can get there, by walking, because I can only move up and to the right. So there's no way I can get to this corner if I go in this direction, right? Because if I go in this direction, am I got to go backwards? Yes. So there's only one way I can get there from A, right? There's only one way I can get there from A. There's only one way I can get there from A. Only moving up, right, or right. And I can't go right on that line. Guess where I'm going next? You have to go in a certain order if you want to see the pattern. Okay? So, how many ways can I get here? One way. How many ways can I get here? 1. How many ways here? 1. How many ways the next spot? 1. So far, so good? So I'm moving. So there's only one direct path to get to all those corners, because I'm trying to get to B following a line. Okay? So now I can start moving inside my block. So how many ways can I get to here? Does everybody see that there's 2? Because you can go up and right, or right and up. There's only 2 ways to get there. Okay. How many ways to get there? 3. Because again, if there's 2 ways to get to where I just said, am I only adding one more spot? Because I can go through 2. Right? So there's 1, 2, 3. Do you guys see those? So there's 3 ways. Oops. How many ways to get to the top? 4. You guys seeing the pattern now? It's a pattern. It hopefully makes sense, guys. From the 2 corners before, you just do what with those 2 numbers? Yeah, 3 times 1 is 4. 1 times 2 is 3. 1 times, or sorry, add them. I said times, yeah. So you're just adding them, right? Because if I can get 1 way to go to here, right, 3 ways to go to here, there must be 4 ways, because I can go 1, 2, 3, 4. So you add the 2 corners behind to get to the next corner. Because if these got really big, right, can I literally take my finger and do all of them if I end up getting a really huge grid? No. I could, but it would be forever. Right? So let's continue. How many ways can I get there? 3. Let's see if we got her. How many ways can I go there? 6. How many ways to go there? Guys, how many? 10. Good. Right, and so on. So then, how many ways to get to here? Exactly 4. And then here, 10. And then here, 20. Whoopsie. And then here, 5. And then here, 15. And then finally, winner, winner, chicken dinner, 35. Well, it used to be part, like we will actually look at this a tiny bit because it's called Pascal's triangle. We do look at it a little bit when we look at the binomial theorem, but not that we have to do that. But this pattern of numbers actually happens when you expand polynomials. Right? So, and again, we'll look at that when it needs to be. So you don't never have to do that in a question. But could I give you any square grid, as many lines in the inside, and I give you specific directions? Yeah. And you can always do this. Okay, this always works. Whoopsie. That always works. Most students prefer to do that. Okay, because it's just quicker. Okay, but do you know how many students forget to do this? So guess what I have students do? They do the box and they do the numbers because somehow they remember to do that. It's weird. Either one, I don't care. All right, so please guys, okay, these little guys here, good textbook questions. They're gonna have more restrictions for you guys because the assignment you guys did yesterday, do you guys agree that those are all very basic? So now, and they're all gonna be muddled together, okay? And tomorrow we start combinations.
It's gonna be Friday, and then we're gonna be home for 4 days. Well, not you, you're gonna go off.
Do you have